Not use the microphone because I will have a short speech. And hi everybody, welcome to our session. I hope you had a good lunch. My name is Philip. I'm working for wayfare for 6 years already. I'm a project manager at the end customers, but also to the application partners. For those of you who attended the grand opening from this morning, you saw that things like quality, code quality in special, and also tools like SonarQube will be handled in the next version of Progress, in version 12. Also, before lunch, it was a session regarding the rules and development using SonarQube. So it's clearly a more intensive, a bigger interest in this subject. This session is not meant to be like real training. You won't receive any diploma at the end and no test either. But it will be like an overview for best practices, definitions in this subject. My colleague Nicoleta will present all this information. For her, I think you will notice, but we will see. It's the first time she's doing this. So please be gentle with her. If you have any tomatoes, I hope you let it at the entrance. Yeah, it's really nice to see our people inside wayfare growing. That's why we are also very pleased to offer them these opportunities. She has also a funny way to handle all these emotions. She starts to laugh a lot. And we could not find any solution to make her stop. So if this happens, it's not you, it's her. Okay, so maybe if I please, a big round of applause to her to have this emotion.
Thank you, and hello again. I know that it's after the lunch time, so if the presentation is boring and you get sleepy, I will blame it on the lunch, so it's okay. I would like to take this opportunity to talk about code quality metrics and their importance in the life of a software product. But first, to introduce myself, my name is Nicoleta Suciu, for short Nico. I am a software developer at wayfare, having 3 years experience in Progress. I would like to think that I'm the typical developer that doesn't jump up at any chance to speak in front of groups. So here I am, being brave. But let's see what we'll talk about today. We'll talk about why the code quality metrics are needed, which are the metrics, how we can use them, and some tools. Good code is like a good joke. It needs no explanation. But we all know that it's not that simple. We aren't born with the knowledge of good coding, so we'll do a lot of mistakes and we'll have a faulty code, let's say. Good code is, creating software is difficult and complex. It can be successful upfront, but be littered with faults and maintenance headaches. So software metrics are a way to predict quality within a system and be able to reduce the potential defects that may appear. And also it increases the ease of maintenance. Good quality code is an essential property of a software product. It can influence the life, the time, and the finances you invest in the development of a product. We all know that in our days, the size and the complexity of an application has increased exponentially, so it is nearly impossible to measure the quality, best practices, and the coverage of the code. So metrics tracking is essential because of the following reasons. You cannot improve what you don't measure. Prevention is better than cure, and what you don't measure you cannot prove. So basically, the metrics will give us an insight in the software, the status of a software product, resulting in a better control. It also can pinpoint us to areas that need improvement and there are a lot of quality metrics and best practices out there. So I will try to break down this complexity to a few general categories, and I will try to cover at least 2 metrics for each category. We'll talk about quality metrics, coverage metrics, object-oriented, complexity, and a more non-conventional, let's say, metric, work that frustrates per minute. So we'll start with the complexity metrics. Having multiple system interfaces and complex requirements, the complexity of software gradually emerged to be huge, becoming too difficult to understand at once. So left unchecked, this complexity will lead to problems when trying to determine the hotspots where risk and cost will arise. So we'll try to cover cyclomatic complexity and essential complexity. Let's see what cyclomatic complexity means. This metric measures the number of linearly independent paths within the source code of your application. So this metric is generally used to measure the complexity at class or method level, where there are a lot of conditional statements. It is not beneficial to measure it at the project because this won't help you to fix the issues in your code. The measure of complexity is based on a graph theory, and we'll see on an example which is the process to construct a flow graph. Okay, so for the first step, you have to break down your code in smaller blocks. So in our example, all the linear independent lines are statement 1, statement 2, statement 4, and so on. And after that, we can construct a diagram which, where basically you transpose the code into blocks. This step will help you to construct the graph much easier. After that, you just have to create the nodes and connect them. So we'll have a flow control graph. How to compute this cyclomatic complexity? We have a formula. I won't insist on it because we don't like formulas, and usually there are tools that compute these kind of things. But if we apply this formula on the previous example, we get a cyclomatic complexity of 5. Usually the cyclomatic complexity is around the value of 10. If you have a higher value, then it means that your code is faulty, is too complex, and it needs to be refactored. The general goal with this metric is to reduce the cyclomatic complexity as much as possible, which will generally reduce the overall complexity of the code. In other words, will give us the following benefits. Reduces the coupling of code. highly coupled code cannot be modified easily and independently of other code. Besides the reducing of coupling, it increases the code readability and ease of testing. For example, if we have a cyclomatic complexity of 5, then it means that we need at least 5 tests to cover all the functionality, all the code. Now we'll get to the essential complexity, which, so through essential complexity you determine how many cyclomatic complexities can actually be removed through refactoring until you get to the fewest possible linear paths in your code. A higher essential complexity usually means more difficulty when using and testing that code. But how can we reduce the complexity? First, we have to validate and remove unwanted if statements. Refactor big methods into smaller ones. Use single responsibility principle to break larger classes to smaller ones. And lastly, we remove the unnecessary or redundant else conditions. But we have to be careful how we refactor. We don't want to break something. So we'll have also an example. Here we'll have a simple do and if statement. While this is a rather obvious example, the idea of essential complexity is to look at a snippet like this and understand that we can remove both the do and the if statements. They have no purpose and the assignment will always be executed. So we'll get to a single linearly independent line. This will give us an essential complexity of 1. As a conclusion to this kind of matrix, we can see the cyclomatic complexity as a measurement and the essential complexity as a solution. What we need to do to reduce the complexity. Next, we'll cover the cycle. So we'll talk about average percentage of faults detected, fault severity and priority, and production incidents. We'll start with average percentage of faults detected, which is the ratio of the number of faults relative to the number of tests in a test suite. APFD can be calculated only when prior knowledge of faults is available, therefore is used only for evaluation. This metric can be applied on used with prioritized or non-prioritized test suites, and we'll see what is the difference between them on an example. But first we'll have again a formula to see how it is calculated, but I won't insist on it. We'll go next to see some values. So for our example, the value of APFD for non-prioritized test case is 0.62. That means that 62% of faults were detected by the test in our test suite. If we want a prioritized test case, then we have to do some additional computation, meaning the rate of fault detection. The rate of fault detection is the ratio between the faults detected by a test over the time it took to that test to run. So applied on our example, we get a value of 0.7. That means 70% of the code of the faults in the code were detected, and we can see that we use the same tests and we get different values. So with a prioritized test case, we get a better coverage of the code. This metric is an easy way to evaluate the quality of specific components in the application and allows you to improve the regression testing. Now we'll go next to fault severity and priority. So not all faults are the same. Some are minor headaches and some can have catastrophic impact on our application. For example, we can have a faulty code that is never executed in operation, and then we can say that our system never fails. Or we can have only one bug that is run at the very start of the application, and then the system will fail every single time. So this kind of situation leads to the need of differentiating between the appropriate failure severity and priority classes. But first, let's see what is the difference between severity and priority. Severity is defined as the degree of impact a defect has on the system. And the priority of a defect is the urgency with which that defect must be fixed. The attributes used to determine the severity and priority of a fault will depend on your organization and business requirements. But even with rudimentary rating applied, it can be much easier to track and fix the faults that are present in your system. The most used classes to categorize the defect, severity and priority are the following. Usually they are intervals between low to critical or high. A low value usually means that the defect doesn't have any major impact on the system, and a critical value, it means a complete shutdown of the system. Priority and severity can be classified in different levels that aid in determining how the defect must be handled. We can have values like high priority and high severity. This means that any critical business case failure gets into this category, or we can have high priority and low severity. Here we have the defects that have an impact on the user experience. For example, the logo of the company is spelled wrong. We also have high severity and low priority, where we have features that don't work but are rarely used. And low severity and low priority, this usually means cosmetic errors, misalignments of paragraphs, wrong font, wrong color, things like this. But now let's see who defines this. Severity parameter is assessed by the tester, whereas the priority is assessed by the product manager or any stakeholder. It is imperative for the tester to choose the right severity to avoid confusion within the development team. Assigning the wrong severity to a defect can have some major impact on the overall performance of the team. Now we'll go next to the production incidents. It is beneficial to measure the production incidents both in number and in their rate of occurrence over time. To obtain more accurate values, it is imperative to record the initial cause of the defect and corrective measures that were taken to solve it. In the case of organization with multiple teams, this metric will provide insight into which team is working well and what team needs some improvement, since the root cause can be often traced to a specific team. The next topic will be about object-oriented metrics, which are focused on measuring the relationships and coverage between independent classes, modules, and the like. and we'll try to cover the coupling between objects, responses for a class, weighted methods per class, depth of inheritance tree, and the number of children. First, we'll have the coupling between objects. This metric was introduced to measure testability, maintainability, and reusability of a class. So we all know that two classes are coupled when methods declared in one class use methods or instance variables defined by the other class. The CBO doesn't care about the direction of a dependency. Coupling can be via method invocation, polymorphism, variable preferences, return types, inheritance, and so on. A use is counted only once, and it can go either way. So the CBO gives insight into important aspects of software design. So high CBO's values indicate a low modularity, reusability, and maintainability of a class, as well as a high complexity. A measure of coupling is useful to determine how complex the testing and the testing will be, and unnecessary interconnections between classes. The next metric is the response for a class. This value is the sum of number of methods called within a method body, and the number of that class becomes more complicated and the complexity will be high. A worst case value for possible response will assist in appropriate allocation for testing time. Now we'll go next to weighted methods per class. This class weighted methods per class metric is defined to be the summation of all methods' complexities. As a measure of complexity, we can use the cyclomatic complexity, or we can give an arbitrary value of 1 to each method. So then the value of the WMC will be equal with the number of methods in the class. WMC can be an indicator of class quality. It predicts how much effort and time is required to develop and maintain a class. Classes with larger number of methods are likely to be more application specific, limiting the possibility of reuse. Now we'll, So we'll have an example with two different complexity measurements. The first one uses the Thomas McCabe cyclomatic complexity, and the alternative, you can have the total number of decision points in the method plus 1. So we have the following values for each method, measured in both complexities. So the WMC for a class will be in the first case 12, and in the second 4 is the sum of the cyclomatic of the complexity of the methods in that class. For the next metric, we have the depth of inheritance tree, and is measured by the number of ancestor classes. A high DIT will indicate high complexity but greater potential for reuse. By observing the DIT metric for classes, we can determine whether the design is top-heavy or bottom-heavy. A top-heavy design usually means that we have too many classes at the top of the hierarchy. And it also suggests that you may not take advantage of reusing the method. A bottom-heavy design means that we have too many classes at the bottom of a hierarchy. One of the advantages of gathering matrix design complexities is that you can adjust the resources between design and testing accordingly. High inheritance will reflect difficulties in testing and maintainability, but higher reusability and understanding of the design. Next, we'll have the number of children. This matrix refers to the number of subclasses that are going to inherit methods of the parent class. High values on number of children usually means that we have an improper abstraction of parent class, misuse of subclassing, more testing for the base class, and higher use for the parent class. Now we'll have the coverage matrix category. In computer science, test coverage is a measure used to describe the degree to which the source code of a program is executed when a particular test suite runs. So a program with high test coverage value suggests that it has a lower chance of containing undetected software bugs. And we'll talk about function coverage, statement coverage, and branch coverage. First, we have the function coverage. The best way to explain this, what is function coverage, is the answer to the question, has each function in the program been called? This matrix aims to measure the quantity of functions, methods, and classes that are covered by the test suite. It's also better suited for testing the actual business requirements. Even though just focusing on functions can be easier, in some cases it may still not be feasible to build tests that cover every functionality in the code base. So if it's not feasible, then what we will do? It's often a smart choice to implement a functional coverage alongside some form of prioritization. This will be similar with the fault prioritization, but except rather than prioritizing faults, you prioritize the functions. You have to figure out which are the most critical to the current release or to the story that is being developed, and prioritize their coverage in the test suite coverage. Next, we'll have the statement coverage. Through this form of testing, we make sure that all of our code blocks are executed. It covers only the true conditions in the method. A good measure of how well you exercise your code is the ratio between the number of executed statements and the total number of statements. The higher this number, the better you exercise the code. But 100% statement coverage is not implying a fully functional testing. Here we have a pseudocode and different tests. To have a full coverage of the code, we have to run all 4 tests to get a value of 100%, or just the last test. The last test will be enough to get us the maximum value. There is also a limitation with this kind of testing. Statement coverage does not tell if the intended functionality of the design is being verified or not. It just tells you if the written code is fully exercised. And further, we'll see some examples to understand better the limitation of this kind of testing. Here we have a method that will have a correct test for this method that passes and gives us 100% code coverage, but still we have a bug in there. This test will give us a full code coverage because it enters the if statement and in the tested method and runs all the lines of the code. It does not, however, give full coverage because the two different cases have to be tested independently. And here we have the correct test. The first one is the one you saw previously and another one. This test, the second one, will clearly show that we have a bug in our code that wasn't detected by the statement coverage, code, because we lacked functional testing. To see what I'm talking about, we can see here that we always return the default value. So it doesn't matter what input value we have, the return will always be the default one. So the statement coverage test will give us 100% because it will run all the lines, but functional, it won't find the bug. The problem, as I said, it was that we lacked the functional coverage. So, as we saw before, to have a full functional coverage, it can be hard to implement or measure. So what would we do if it's not feasible to write covering tests to the code? So we have to make sure that we have written a test at the beginning of the implementation that it will fail. And after that, we'll write the code. So we'll have a test-driven development. And that will ensure that all the new functionality is covered by the test and without getting a lot of redundant tests. Another form of coverage metric is that of a branch coverage, which aims to measure how many branches in the code base have been executed during testing. It covers both the true and the false conditions, unlike the statement coverage. The decision coverage can be calculated as given below, and as we saw before, just one test case was required to achieve 100% of statement coverage. However, the decision coverage requires each decision to have both a true and a false outcome. So 100% statement coverage does not imply full branch coverage. We have again an example. To achieve 100% of decision coverage, a second test case is necessary. It is important to note that 100% statement coverage will not give us 100% branch coverage. For 100% branch coverage, we'll have to run both tests. And now, after we cover some of the important coverage metrics, we'll talk about a more unconventional metric, and it is about work that flash rates per minute. which is basically the code review. So reviews aren't a form of punishment, but a stimulant for us to properly complete a task. We don't like to admit that we make mistakes, and we do a lot. And we certainly don't realize how many we are doing, because otherwise we will correct them ourselves. So doing a peer review can have a major impact on the quality of the code, as well as our professional development. This simple action is one of the most powerful tools available. Some research was done, and the results are the following. We get only 35% false detection for function testing, 45% for integration testing, 25% of unit testing, and the code review 55%. So we'll go now to this part. When we do a code review, we can hear some strange noises, some reddening faces, maybe smashing some keyboards, mouses, I don't know, or maybe quitting for the day, or week, or month, or forever. And I can say that that is a true statement. Like, we do a code review for one day, and you're getting nervous, and you just go home because the code is really bad, and you don't have the patience to stay and understand it. So, how can you control these WTFs per minute? It's just regular code reviews, ongoing educations, and mostly learning from your mistakes. So going next to the tools. There are many tools out there to analyze the code, but for Progress, the most complex one is the SonarQube, and I think that you heard about it in the last 2 days a lot. So I won't say much about it. It's an open source platform developed by SonarSource. The OpenEdge plugin is developed by the Riverside software. It supports 20+ programming languages and has 50+ official plugins. This tool, you have a dashboard that will give you information about securities, vulnerabilities, bugs, code smells, coverage of the code, and so on. So for code quality metrics, it can say to you if you have duplicated code, lines of code, technical depth, code coverage, comments density. And from what I understood, there are no free rules available, so you have to pay something to get this, or you can write your own rules, because it is an open source. So next, the conclusion part. What tools to use, what metrics to focus on? Well, that depends only on the type and the size of your project, the people involved, and the time you want to invest into and into a better quality of the end of the product. So we're getting to the questions part, if there are any.
I
No yet. No. Yes.
That means, do you measure that measurements in your development process today?
If I'm
Do you measure that KPIs within your development process today if you don't use SonarQube?
No. We usually do the code review and some unit testing. I'm working for outsourcing companies, so I'm somehow limited by the needs of the client. Any other questions? Okay. If not, then thank you for your presence.